All right, so here we are now in Unit 8, Fingerprint Analysis. So we're quite a way into the course now, but we'll be talking about some things that we mentioned way back in the beginning, so hopefully you're fresh on that as well, as we explore the wonderful world of fingerprinting. Okay, so way back when we talked about our friend Alphonse Bertillon. He was one of the important historical figures in the development of forensic science, and we talked about his system, anthropometry or anthropometry, however you prefer to say it. It's a failed system, so I don't think it's going to matter if we mispronounce it by Bertillon standards. And as you recall, it was a system based on several bodily measurements, so things like arm length, ear width, finger length, head circumference, things like that unfortunately do change with time, right? Especially if you think back to when you were a little baby compared with you as an adult, and even into old age, those measurements do vary. And so it probably wasn't the best system to go with, but it was used extensively from about 1882 until 1914, and the most common place it was used was for prison records. So this was again a system that we had a lot of confidence in, and as we'll find was probably misguided. Mainly the biggest problems with it is that the measurements were not unique, as we'll talk about in a moment, and as I already mentioned, they change with age, right? Within an individual, they change from infancy through childhood, adulthood, even into the elderly years when things change a little bit as well. So again, I applaud Bertillon. He was wise enough to recognize the need for a system that would identify individuals, but unfortunately his system of choice did fail. After just over 30 years of use, it was discontinued because it just didn't provide what was necessary for the individual identification of people. So the text mentioned some other individuals, and again, they were important, but compared to our friend Francis Galton, they were relatively minor in terms of taking Bertillon's system and moving it toward the current personal identification by fingerprinting. So lots of things happened, and we should understand that, but it was really our friend Francis Galton here, who was familiar with Bertillon's system, but also understood the importance of fingerprinting, that allowed it to become the quick replacement to Bertillon's system. Even before it really failed completely, Galton was championing the idea of fingerprinting for individual identification. So he's best known for his book Fingerprints, which is again the first book specifically on this. There were historically there were people, even thousands of years ago, that were making use of fingerprints for personal identification, but in terms of the modern idea of forensics, we have Galton to thank if we want to point to a single person, again recognizing that no single person can make progress without others who've come before. So what did Galton do that was so special? Well, he showed that prints are unique, permanent, and don't change with age. So they get bigger as the individual gets bigger, but the print itself doesn't change. So no two people have the same prints. That's our unique idea. You can't really damage them. You can get scars on them, certainly, but that makes them even more individualizable, because no other person would have a scar in that position on that print. And finally, again, the biggest problem with Bertillon's system was that it did change with age, while this idea of fingerprinting does not change with age. So he also identified and named the minutiae, which were called, Galton's characteristics way back when. Now they're also known as ridge characteristics. We use those terms interchangeably. So minutiae, which is Latin for the small things, or ridge characteristics, which is a little more descriptive of what we're talking about here. Those terms are used interchangeably. So just know that by saying one, we mean both. Okay, so while the Bertillon system was in use until around 1914 in at least some places, a lot of places had started moving away before then. So if we look here at 1902 in New York State, the individuals taking the New York Civil Service exam had to be fingerprinted, and they were fingerprinted multiple times. They were fingerprinted when they submitted their application. They were fingerprinted when they took the test. Let's say they had to be able to type a certain number of words per minute. So what could be done by some unscrupulous individuals would be to submit an application and then have a friend or family member who was better adept at typing take the typing test, for instance, and then once you got the job, it's difficult to remove civil servants without, again, a fair deal of due process. And so at that point, you might end up with someone who types like I do, and it's maybe 10 or 15 words a minute. That's not desirable, so it's not honest. It's certainly something that the civil servant exam was intended to screen out those people who don't have the requisite skills. So now that you're identifying people with fingerprints, then you know that the person who applied and took the test, and then finally they'd be fingerprinted when they showed up to work, you know that those three fingerprint matches would indicate that it's the same person who did all those things. So that was one of the first uses of fingerprinting for personal identification, especially in a civilian sense. The next year, 1903, New York State prisons stopped using Bertillon's anthropometry because of the William West incident, which didn't happen in New York, by the way. It was at the Leavenworth Federal Penitentiary in Leavenworth, Kansas, or just outside of Leavenworth, Kansas. And so that was a situation where the two brothers, they were never determined to be brothers. They're believed to have been twin brothers, but they were sent to Leavenworth at different times. One was named William West and the other was Will West. And so when Will West showed up at Leavenworth, they looked at his measurements for Bertillon's system and realized, based on his picture and measurements, that he was a match for William West. So they assumed that William West was able to escape and then was recollected. So when they went to William West's cell, they were shocked to find William West in his cell. So that was a big indication that the Bertillon system had broken down. You had two individuals who, again, may have been twin brothers. They may not even have been related, but certainly by appearance here on the slide, they certainly look like they could be twin brothers. But regardless, whatever their relation or non-relation was, they had the same Bertillon measurements, and they had the same physical appearance, and they were in a federal prison for different crimes with different times to serve. So there needed to be a way to keep them separate and identified, and lo and behold, fingerprinting provided that answer. So whether or not they were identical twins, even identical twins and everybody else has unique fingerprints. So that made another case for the idea of using fingerprints as opposed to Bertillon's system for individual identification. The case of the William West incident led the federal prison at Leavenworth to have all inmates fingerprinted starting there in 1904. And then by 1924, it was still the Bureau of Investigation at the time, but what we know now is the FBI, Federal Bureau of Investigation, began housing all fingerprint information at the federal level. And then about 80 years later, we have the Integrated Automated Fingerprint Identification System, IAFIS, which is the federal level system, which again holds millions and millions, 70 million, over 70 million prints now. And those prints are not only just the fingerprints, which again, we shouldn't say just, they're very valuable, but it also will include other details, like if there's tattoos or scars or any other physical appearance personal identifiers. It'll have a picture, it'll have aliases, it has a trove of information. So it's again computerized, so not only is it fast to search, but it also includes a lot more than just the fingerprint identification information that you would expect in a system like that. All right, so I hinted at it just a moment ago when I talked about how fast it was to search AFIS. Now, again, just general AFIS refers to automated fingerprint identification systems, and these could be local, these could be state systems. Again, IAFIS tends to be the acronym we use for the national database at the FBI, but any of those would fall under what's called automated fingerprint identification systems. And these started in the 1960s when you had over 1 million prints and you had to search them, right? If you found a print at a crime scene and you wanted to see if it was someone who was already in the criminal system database, then you would have people laboriously searching through these fingerprint records, and that would take an incredible amount of time. And so it was, shortly after the widespread use of computers that law enforcement realized that there had to be a better way that involved the use of computerized searches of these records. So the 10-print subsystem uses fingerprints obtained while a person's under arrest. The fingers and palms are scanned, and then if we're looking at when they're booked into a prison, that's usually able to get really high quality prints because you have control over the situation. If the suspect moves or it's just excessively sweating or not giving rise to good prints, then you can reprint the person right there. So those prints that are the known prints in the system tend to be very, very good. And so if you're looking to scan someone, even for civilian purposes, where you have the fingers and palms scanned there, you can complete an AFIS search in about a minute or less if you're looking to see, for instance, for applying for citizenship or green card purposes. We need to search and make sure this person's not a wanted fugitive. So it's a very quick search to see if any of those digits come up with any matches. And again, it shouldn't alarm anyone if one or two does come up with what the system thinks is a match, because ultimately it's a human expert that would identify that. But again, if all 10 fingers come up with a match with our 10-print subsystem, that's very concerning. So matches get sorted by a technician to verify if it's a true match or, again, if it's just close. Computers have come a long way, certainly from the 1960s, so you have fewer of those matches that are really off. But in the early days, the computer was looking for something that a human eye would obviously catch if there's not a match, but the computer would bring back what it thought as close matches that an expert would never have mistaken. But fortunately, again, the state of the art is really, really impressive now, and you get very likely matches when the system identifies matches, but it still needs to be verified by that fingerprinting expert to make sure that it is indeed a match. All right, so in our last slide, we were talking about if there was a person who was, again, it could have been a civilian purpose or more likely, and of course, like this, we're talking about individuals who are being booked for one crime, and we want to check and see if they're fugitives for another crime. Well, in those situations, you tend to have, again, as long as the individual has all 10 digits, you have all 10 digits to be able to check. At a crime scene, that's unusual, right? If you're looking at a latent print or the criminal identification subsystem, we're looking at those prints that a perpetrator left behind without knowing at a crime scene. So we've got some issues there, and we'll talk about those later on in this lecture, but usually they're not perfect, right? Because the individual didn't even know or intend to have those prints. They're not usually able to be developed perfectly like the prints that you can roll in a controlled police station environment. So these can take longer for these searches because the latent print itself may not be of the highest quality. So these can still take minutes to hours to days to search. The technician, again, determines if the closest match are indeed a match, and again, it's just more labor intensive even for the computers of today to be able to take a look at a single digit and search it across all the known prints in the criminal database. So especially since that single digit may not be a complete print and may not be the most legible print. So it's still impressive and still certainly a lot better than having humans pouring through pages and pages and pages. But again, it does take some time, especially if we're looking at just a single latent print for identification. Another of the problems with the automated fingerprint identification services is that cities, counties, states purchase different computer programs. Again, competition is great, and it's one of the hallmarks of our approach to competition and bringing price down, but it also can lead to some problems. And so it's nice that they can all communicate, at least the state systems can each communicate independently with IAFIS, but they can't communicate with each other. So state A, their state level system and certainly their local level systems cannot communicate necessarily with each other, but they can all go upstream. So a local AFIS can communicate with its state AFIS, which can communicate with the federal IAFIS at the FBI. But a drawback, of course, is that a local W and local X can't necessarily communicate with each other, and state A and state B can't necessarily communicate with each other if they purchase different computer programs at the time. So that's something that hopefully will be addressed in the future, and there'll be total interoperability from local to local and state to state. And of course, from state to national, the IAFIS should remain interoperable. But it's something that, again, hopefully will be resolved in the future. But at the time of this recording, there's not a resolution nationwide on having all the states be able to search each other's or local systems be able to search other local systems even within the same state. So something for the future, which hopefully won't take forever to accomplish. Okay, so despite those problems, again, the individual automated fingerprint identification services and certainly the IAFIS integrated automated fingerprint identification system at the FBI level are quite impressive, and they are able to give a lot of information. As I mentioned before, IAFIS, if you get a positive result there, which sometimes you'll get multiple, and then the technician will decide if any are indeed truly positive IDs. Well, in addition to IDing the person by the print, they're going to have access to criminal histories, photos, physical characteristics, aliases, scar and tattoo information. Again, all things that are helpful in law enforcement pursuing that suspect. And again, at the time of this recording, we're looking at over 70 million records and 34 million civilian prints. So that's, again, a huge number, and it's only growing, unfortunately, because of more people entering into the criminal justice system and being fingerprinted and added to the database. So a quick response time, well, 1 to 24 hours is pretty impressive for that number of records, because the old system of looking them up by individuals scanning through the prints by hand would take considerably longer. That's an understatement. So again, computers keep getting faster, but we keep getting more records. So that response time is fairly accurate, at least at this time, for how long you could expect an IAFIS search to take. But nevertheless, it's still pretty impressive, and again, within a day to be able to have that information is quite helpful. So why are these fingerprints so persistent? Why do we consider them permanent for an individual? Well, we have to know a little bit about skin anatomy to answer that question. And again, we're going to keep it fairly superficial here. So the very topmost layer of the skin is the epidermis. That's the protective layer of skin. That's what we're used to when we think of skin. That's the layer we tend to think of. Underneath that is the dermis, and the dermis has a lot of different functions. It helps control body temperature. It's giving the skin its flexibility. It provides that epidermis with nutrients through blood vessels that travel very close to the top of the dermis and allow for the epidermis to reap the rewards of the nutrients traveling through those blood vessels. And at that top layer of the dermis, we've also got the dermal papillae. So that's the upper layer of the dermis. It's just below the epidermis. And so that's what gives the patterns of the fingerprint ridges. And that's why it's so difficult to damage those. You really have to go down below the dermis into that upper layer of the dermis and damage that. And that's really hard to do. Again, it's possible, but you have scarring as a result of going that deep. And as I mentioned before, a scar is probably even more individualized than a ridge characteristic for an individual. So it doesn't really help to, achieve the goal of making the person unidentifiable by fingerprints. It probably makes them even easier. So finally, we should mention the hypodermis. That layer below the dermis is made up of fat and collagen. It insulates the body. It helps to be a storage there, long-term storage of fats if the body needs to go into those supplies for energy, if the individual has gone a while without eating and needs to supplement that with some of that stored fat. So hopefully this crash course in skin anatomy helps at least orient you in terms of where that ridge characteristic pattern gets propagated, and the fact that it's in the dermal papillae would indicate that it's quite deep below the epidermis, and therefore something that's going to propagate and be permanent throughout the individual's lifetime. Okay, so we touched on some of these fundamental principles back when we talked about our friend Francis Galton, who we credit with being the real modern champion of fingerprinting, although again he certainly benefited from earlier work by others. So the first of the fundamental principles is that fingerprints are an individual characteristic. So as we looked at with the William West Leavenworth prison example, we can't be sure those two were identical twins or even brothers, but if they were, even identical twins will have unique fingerprints. So that's important when the Bertillon system had those two gentlemen as identical. Fingerprinting was easily able to distinguish the two men. So even identical twins will have individual fingerprints because, and this leads us right into number 2, fingerprints do not change over time. Not only do they not change over time, they're also determined fairly early on. So even these identical twins who share the same womb could certainly and statistically will develop different prints because the dermal papillae, that lower layer of the skin that we just mentioned, the upper layer of the dermis beneath the epidermis, is where the fingerprints are formed, and those are formed by random movements in the womb during fetal development. So before birth, your fingerprints are already formed, and again, it's such a random process that even two siblings sharing a womb, identical siblings, would develop unique prints. Finally, the third fundamental principle, and why fingerprinting is such a nice method for personal identification, is that fingerprints display patterns. And so we have the ridge characteristics that we'll talk about, but even more easily distinguished, we have just 3 major patterns. So loops, whorls, and arches. So loops are the most common. They account for about 60% of prints. Whorls are less common there at about 35% of prints, and then finally arches are the least common at about 5% of prints. Now again, an individual can have loops, arches, and whorls across their 10 digits, but they're not able to have more than one on any given digit. So each finger is going to be a loop, an arch, or a whorl, and statistically speaking, loops are the most likely prints, and we'll talk about the types of loops in a moment. So about 25% of the population has no whorls at all, even though we see whorls are about 35% of prints because it's not necessarily an even distribution. You get about 25% of the population has only loops or arches, and that means about 75% of the population has at least one whorl. One of their fingerprints is a whorl, or maybe more. But again, an arch is the least common of all, but still, statistically speaking, about 1 out of every 2 people, or at least 1 out of every 20 prints should be an arch. So that gives you an idea of the distribution in the current population. So since they're the most popular type, let's take a look at those loops first. So when determining the pattern, whether it's a loop, an arch, or a whorl, the first thing to do is locate the delta, if any. So if there's just one delta, and we have that in the lower left of our image there, you see it looks sort of like a triangle. It's the Greek letter delta, looks like a triangle in its Greek alphabet form, so that's why we give it that name. So if there's one delta present there, then you have a loop pattern. Okay, so now the loop itself will tend to lean one way or the other, right? If it was perfectly symmetrical, then you wouldn't have a delta and you wouldn't have a loop, you'd have an arch. So since the loop is going to lean one way or another, we have to consider how the ridge enters and exits. So in this example, we see the loop comes in, it travels in from right to left, and then loops up and then goes down and exits from left to right. So since it came in on the right side, it left on the right side, and if it points toward the pinky, that would be the ulnar style loop. If the loop exits toward the thumb, then it would be what's called a radial loop. So if we assume that this particular image here is a right middle finger, then if we consider the right middle finger having its loop here coming and going from the right, then that would be the pinky side of things. So this would be an ulnar loop if it's indeed a right middle finger print. So to make that a little more clear, I hope, we have this image here. So looking at first, this is a right hand, as we can tell, based on the palm side up. The thumb would be on the right for a right hand as we look at it. So the ring finger, we see an ulnar loop. So if we look at the large version of that print, again, we see just a single delta, which tells us we're dealing with a loop. We see that it comes in from the left and then goes out to the left. And since on your right hand, that would be the pinky side of things, that's going to be an ulnar loop. So that one there for the ring finger for this individual, based on that large cartoonish example, would be an ulnar loop. If we look at the middle finger on this individual, again, it's the right middle finger, just like I had mentioned in the previous slide. We see the loop coming in from the right and then going back out to the right, and for the right hand that means it's going to be pointing toward the thumb on its exit, and that's a radial loop. And again, they come from the radius and the ulna, the bones in the arm down below, which is why we get that. The ulna is the bone closer to the pinky, and the radius is the bone closer to the thumb. So hopefully that helps to clarify that. If you're having trouble distinguishing radial and ulnar loops, then please don't hesitate to reach out for some clarification. But hopefully, once you identify a loop, getting that idea of radial versus ulnar, as long as you know which hand it's on and whether it's coming in and out from the right or the left, it shouldn't be too difficult. Now, as we move on to whorls, I just want to mention about those loops. The ulnar loops are far more common than the radial loops, and even the position there does make a difference. Radial loops, again, which are the more rare types, tend to be on 4 fingers, whereas ulnar loops tend to occur on the other digits. So looking at whorls, again, we have a distribution there as well. So whorls will now have 2 or more deltas, whereas the loops had just a single delta. So the plane whorl, which is about twice as common as the central pocket whorl, has 2 deltas parallel to each other with a large circular pattern. And if we were to connect the 2 deltas with a straight line, we should cross through that central circle pattern. And so we see that on the image to the right, whereas a central pocket whorl has 2 deltas that are not parallel, and therefore when you cross those, when you connect those 2 non-parallel deltas, you will not cross through the circle pattern, which tends to be a smaller circle pattern in the middle. So they're both classified as whorls, but again, the plane whorl is the much more common type. The central pocket whorl is less common, and it gives rise to that smaller circle pattern and the uneven deltas. Finally, looking at some other less common whorl patterns, you could have the double loop whorl. So that's going to have 2 deltas, and then there's going to be 2 loops that make an S shape in the central pattern. That simple whorl, plane whorl rather, would have just a simple circular shape. So don't classify this as a loop, even though we call it a double loop. It's a whorl, so be careful about that if you're trying to identify prints. And then finally, an accidental whorl will have, again, 2 or more deltas. That's how we're going to tell it from a loop, right? And that's why the double loop above would not be a loop characteristic, because it has clearly 2 deltas there. The accidental whorl would also have at least 2 deltas, and then 2 patterns. It could be a loop and a whorl or an arch and a whorl, but again, it's fairly uncommon, but still would be classified as a whorl rather than the loop or arch that might be present as well. So just be careful on that. Whorls can sometimes be mistaken for other patterns because they may have other patterns inside, but they'll always have at least 2 deltas. And now the final major classification in our loop arch whorl world is the arch. So arches should be most easily identified by the total absence of deltas. So a loop would have 1 delta, a whorl would have 2 or more deltas, and an arch would have no deltas. So hopefully that makes it relatively easy to identify the 3 different types, at least to the level you'd be responsible for here in this course. They tend to look like hills, so a plane arch would have the ridges enter in on one side and then exit the opposite side. And that would be distinguished from a tented arch, which is going to have more of a spike in the middle. So plane arch is going to be more rounded, whereas the tented arch is going to have more of that spike appearance in the middle. And again, it's about 4 times as common to find a plane arch as a tented arch. So that gives you an idea of how rare those tented arches are, because already the arch is about 5% of prints, the least common of the major fingerprint patterns, and again, a tented arch would be only a fifth, 20% of those prints. So that's going to be a relatively small number. The last thing I should mention before we move on from this idea is that there's also racial variations in these 3 fundamental patterns. So people of African ancestry tend to have more arches, even though, as we said, the arch is a fairly uncommon print. And if you look at it, about every other person should have 1 arch. If it was a normal distribution, it's not a normal distribution. You tend to see more arches in people of recent African ancestry, whereas people of recent European background will tend to have many loops, and then people of recent Asian background will have a higher frequency of whorls. So just another thing to keep in mind as you think about fingerprinting. Now, if we want to just think about what fingerprints are, again, it doesn't matter if it's a loop, an arch, or a whorl. Why do we have fingerprints at all? Well, it's a friction ridge, right? It's raised ridges, and it gives us grip. So evolutionarily speaking, it's an advantage. If you think about the gecko that has a lot of ridges there and can basically walk on glass, walls and ceilings and things like that, we're not quite there, but we do have some additional grip. And this is probably a good time to mention that there are people in the world who do not have friction ridges. They do not have fingerprints. It's quite rare, but it does happen. It seems to run in families, and again, it does put them at a slight disadvantage because they can't grip things as well as those of us with fingerprints. Now, it seems like a superpower, right, that they would be able to commit crimes and not be found. At least in the U.S., those individuals, as rare as it is, but there are some individuals that do not have the friction ridges. They're known to the FBI and probably get regular visits just to make sure no one's coercing them to do anything illegal because of their special talent. But again, this probably causes them more headache not having the better grip of the friction ridges than the notoriety of being one of the few people in the world who has no friction ridge fingerprints. So let's talk about the overwhelming majority of us who do have them. Well, the ridges have various characteristics, ridge characteristics, also known as minutia, right? We use those two terms interchangeably here, and so we'll talk about each of these in turn. Bifurcations, ridge ending, short ridge, dot or island, enclosure, spur, crossing, and crossover. All right, so the first term may seem a little off-putting, right? Bifurcation, it may not be a term you've heard before, but if you just keep that first two letters in mind, bi, right? So a bicycle is a two-wheel vehicle. So a bifurcation is where a single ridge splits into two. So as long as you can keep that in mind, then hopefully the term bifurcation, which may sound fairly specific, again, if you can keep the general idea of one splitting into two from the bi part of the bifurcation, then hopefully you'll be in a good place for any questions you might see on the exam on this particular ridge characteristic. Now, hopefully this one's even easier. Ridge ending is pretty self-explanatory. It's the point where a ridge ends. So if we look over at the left there, the lower left at the bifurcation that's highlighted that we just talked about, if we follow the right side of that bifurcation, eventually it just ends, and that would be known as a ridge ending. So nothing too elaborate here. What you see is what you get, and a ridge ending is just what it sounds like. It's the point where a ridge ends. All right, moving on, we've got the dot or the island, and this is a ridge characteristic that's just about as wide as it is long, so it gets that term of island or dot because it tends to look like a dot or a small island. So hopefully that one's another that's pretty easy to take the name and figure it out based on a highlighted area of a print like you might need to do on the exam. Okay, and the last type that we have identified on this particular fingerprint pattern is the enclosure. And so an enclosure is actually a ridge, a single ridge that bifurcates. It splits into two ridges, and then those two ridges rejoin to reform a single ridge. So an enclosure is sort of, if you want to think about it as two bifurcations that meet up again, that's probably a good way to think about it. And of course, an enclosure forms a little loop in there that you could theoretically store something, right? So if you think about enclosures being mailings, things put into envelopes and things like that, maybe that'll help you as well. But however you remember it, that would be the ridge characteristic known as an enclosure is going to be a ridge that splits into two and then reforms a single ridge later on. All right, so now we've moved on to a different appearance of a fingerprint, but at least we've come back to a nice, familiar, self-explanatory name. So a short ridge. A short ridge is a single ridge that is short. Again, for our purposes, that's about all we need to say. I'm sure the FBI has guidelines as to how long a short ridge can be, but again, for our sake, we won't worry about that for this introductory course. But if we look there over at the top right where we see short ridge, it points to that relatively short looking ridge. Again, it's going to be bigger than a dot or an island. It's going to be, have one dimension that goes on significantly more than the other, and that's how we could distinguish it from a dot or an island. But short ridge is that sort of ridge characteristic that's highlighted there. Okay, so now if we take a look toward the center of this print, we'll find a spur, which is a bifurcation. So it's a single ridge that splits into two, but one of those ridges ends after a short distance, whereas the other continues for a little longer. So if you know your cowboy boots, so they had the spurs there to help with controlling their animals, but bone spurs have a history of causing pain to their patients who have them, but actually modern medicine suggests maybe it's not the spur itself that causes the pain, but certainly looks like it might be painful if there was a bony growth on one side of a bone. But again, however you remember it, whether it's the cowboy boots or the bone spurs, that's your characteristic known as a spur, a single ridge that bifurcates into a very short distance spur side and a longer distance ridge. All right, now the last two that we're going to call out specifically are going to sound similar. So the crossover is a short ridge that runs between two parallel ridges. So if we look here at the over on the left side of the print now, top left, we've got the crossover or bridge highlighted, and you can see it joins those two parallel ridges like a bridge. So it's known by both terms, either crossover or bridge, and that's the name for that ridge characteristic or minutia feature known to connect those two parallel ridge systems. All right, and finally now we have a crossing, which sounds a lot like a crossover, but it's a different. It's where the ridges form an X, or really more appropriately the Greek letter chi, right? Which is where we get that letter that would form crossing or cross in Greek. Looks like an X chromosome. And so you have the ridge characteristics appear to sort of swap at that central point of the crossing and move over from left to right. So crossover is the bridge between two parallel ridge systems, whereas a crossing is where the ridges seem to cross each other. So hopefully that will allow you to keep those two separate. Should I be cruel enough to ask a question that's looking for one or the other and both terms are present? Don't expect that. I probably wouldn't do that, but hopefully you would be able to pick it out even if I was that cruel. And so here we see a slide that has an image to sort of highlight those key features that we talked about. Again, there's some things we didn't mention. Trifurcations exist, they're rare, but the bridged, it doesn't talk about the other name, crossover, for that feature. It gives us a new name, hook, for a spur. So just as long as you're familiar with the terms that we identified and called out previously on those preceding slides, then don't worry about anything new or different here. Just thought I would show this image to give you a little more examples of the basic and composite ridge characteristics, which again, ridge characteristics, that phrase is equivalent to saying minutia. Okay, so back to our idea of why fingerprints are so important. What are these things called fingerprints and why do we care so much? Well, a single fingerprint, if it's a complete print, will contain over 100 of these minutia, these ridge characteristics. And we just talked about, again, a fairly good sample of the types, but not a comprehensive list of every type of fingerprint ridge characteristic or minutia example. So most crime scene prints will be found in segments. We mentioned that before, and that's why it takes longer to search for a latent print in the system than to search against rolled prints. 8 to 16 minutia would be needed to correlate between two fingerprints. And again, our friend Edmund Locard, who was a fingerprinting expert, has given us the idea of about 12. A dozen minutia should match in order for us to believe that that print is a match for the individual that we've identified. So again, you can see sometimes less than 12, so as little as 8 if you're, a very experienced fingerprinting expert, then maybe you can make that determination based on only 8. If you really want to be very comprehensive about it, 16 is a safe way to go, but right in the middle there at 12 is where our friend Locard has said is the sort of the sweet spot. You also have the idea of the prints being permanent was one of our tenets of fingerprinting, right? Our fundamental principles as to why it's such a useful way to look at individual identification. So if you do try to damage them, they will grow back or they'll form scars that are characteristic. And as you'll see in our case study, John Dillinger is a former FBI most wanted individual who was killed after he was apprehended or attempted to be apprehended and killed in the ensuing chase. But even the painful acid burning process he went through to try to destroy his prints, he still had sufficient visible print on examination of his autopsy to identify him positively based on fingerprinting. He had gone through plastic surgeries to change his appearance, so the fingerprinting was really the best way to identify him, even though he had had his finger tips burned with strong acid to try to damage those beyond recognition. It did not work. They did grow back sufficiently to identify him based on fingerprint ridge characteristics. And as we can see in this slide, here's an example of a scar that's formed across those fingerprint ridges, and it does give, again, very recognizable appearance. Not anybody would have had the same print before the scar, and certainly no two people are going to have a scar like that in the same position on that digit that we've identified here with the scar and then the detail inset from that scar. So trying to damage your prints intentionally to make yourself less identifiable is not a good idea. It's only likely to make you more identifiable. Again, certainly people can have accidents and get scars on their finger pads, but to intentionally go through that pain is not advised, since it's going to make you more identifiable rather than less so. So hopefully now that you've been sold on the idea of why fingerprints are such a good means of personal identification for those who have them, which is the overwhelming majority of the population, let's talk about the different types of prints that might be found at a crime scene. So the first type we'll talk about is the least likely type to find, patent or visible prints. These could be made by dirt, paint, blood, any of the substances that might be present at the crime scene that could leave a visible print behind if the suspect or the victim were to press his or her fingers into that material. So the reason they're relatively unlikely to be found is most criminals know that fingerprints would be a means of personal identification, and they would try to clean up any visible prints so that they would not be found. The most important exception would probably be a crime of passion, where the person didn't intend things to go that far and panicked and just rushed off the scene and didn't try to clean up after him or herself. Again, a career criminal would likely be wise enough to clean up any patent or visible prints. Plastic prints would be prints that are formed by impression on a soft surface. So the surface deforms as the print is pressed against it and leaves behind a plastic print. So examples of surfaces that would do that: wax or gum, butter. You just have to be careful that the butter doesn't melt and become unrecognizable. Those would be examples of plastic prints. Maybe even if you had made a print for your parent in some plaster of Paris when it was still soft, and then it hardened and became a treasured keepsake. That would be another example of a plastic print. Finally, the most likely type that you would find at a crime scene is known as a latent print. So, right, we have patent, meaning visible, and latent, meaning hidden. So these can't be seen with the naked eye. That's why the criminal would likely fail to see that they were there and clean them up. They're made by the oils, grease, sweat in our fingerprints, and that's what leaves behind that latent print. Since you can't see them with the naked eye, they have to be developed with either powders or chemical developers and then photographed and lifted for later identification. Okay, so just to follow up, here's an example of a visible print. Again, let's assume that that's blood, although it's probably red paint, since this was a print that was made for showing as a visible print. So either way, we'd consider it a visible print because it's obvious, and in either of those materials, if it's a thin layer of paint or of blood, we would consider it a visible print in either of those materials. And here we have an example of a plastic print, again, more of a keepsake style print like you might have made for a mom, dad, some grown-up who was special to you back when you were a child, or even today. You know, if you're looking for an inexpensive and thoughtful gift, then plaster of Paris is a good way to capture some part of you, fingerprint or a whole handprint if you get a big enough piece to share with someone. And again, it's relatively inexpensive but thoughtful and welcome. If it was even a really thick layer of paint, then we might consider it a plastic print. So again, it really depends on the material and the fact that the material will deform and leave the print visible afterward. And finally, here we have an example of a latent print on a smooth, hard surface, and it's been developed with some fingerprinting powder. So we'll talk a lot more about latent print in the remaining slides. Okay, so with latent prints, the first task is, of course, to find them. So you can use a light source to find a print, whether it's a LED, laser, fluorescent, UV light source. Again, a lot is done now with alternate light sources to even hone in on the print and photograph it before applying either a powder or a chemical developer. So finding the print is job number one. Then, depending on the surface, it's either going to be a physical powder or a chemical method to capture that print. So if it's dusting with a powder, that's again useful on non-porous surfaces. So plastic, glass, painted surfaces, vinyl, these are all examples of non-porous surfaces. After the powder's been applied, the print can be lifted with adhesive plastic with tape. Again, you have to be careful if it's a rough non-porous surface that you grab all of that dust, and you can use special lifting methods there. Magnetic powders work really well, especially on surfaces that you don't want to damage the print. So the magnetic powder doesn't require a brush to go on. You can just drag with a magnetic wand. Drawback is you can't use this on an upside down print. The magnetic powder doesn't work in that setting. Finally, fluorescent powder. These are nice because they'll glow under UV light. You don't want to use too much, so it's a nice sensitive method. If you use just a small amount, it can really visualize a print on a non-porous surface. Finally, the chemical methods that we'll talk about, these will have use mainly on the porous surfaces, rather, since we tend to use the powders on the non-porous surfaces. So things like paper, cardboard, wood, materials that have significant pores, holes inside, would be more amenable to chemical methods. Looking at those chemical methods, ninhydrin is the one we'll look at first. And the ninhydrin test works very well because it's attracted to amino acids in the sweat, and it turns that print a bluish purple color. So it can, very easily visualize that print, and it doesn't need to be a fresh print. It can look at prints that are quite old. The drawback is it may take some time to develop. So that's both a benefit and a disadvantage here of ninhydrin as a chemical method. Looking at our next method, iodine fuming. Here the crystals of iodine will become gaseous, skipping that liquid phase. So this is known as sublimation. The solid crystals sublime directly into the gas phase, and then they attach to the oils from the print. So they selectively attach there, and you can get a really nice image of the print. So you can place an object that is likely to have a print into a chamber and heat it along with the iodine, and the print will become a yellowish brown. You'll photograph that print because it does not last forever. If you do need it to be fixed a little longer, then the spray starch can be added. That'll keep it there for a few weeks or months, but again, it's still not permanent in the long-term sense. But because it works on porous surfaces, this is a good method for paper, right? People may not realize that when they touch papers, they leave behind latent prints. And not all the methods will develop on paper, but iodine fuming is one that will. And again, with the starch added, you can have that print preserved for at least a few weeks, if not months. Now looking at silver nitrate as the method, again, silver nitrate works like a lot of these to identify different substances in that fingerprint sweat or oil. In this case, it's salts in the sweat that attract the silver nitrate and form silver complexes. The silver nitrate's mixed with water and then sprayed onto the print and placed in the sunlight to air dry. The print will become a grayish black color due to the silver chloride that forms from the salts in the sweat. It is a destructive method, so it should be used as a last resort, but it does have the advantage of being able to develop the oldest prints compared with ninhydrin and iodine fuming. If those methods fail, it's still possible that an older print would be developed by silver nitrate that had not developed by iodine fuming or ninhydrin. So it's again, it can be destructive, so we don't want to go to it as the first choice, but in a last resort scenario, if you have reason to believe there's a print there that's just not developing by those other methods, then it's certainly worth a try with the silver nitrate method. Now finally, let's talk about cyanoacrylate fuming, because this is a chemical method that tends to be combined with the physical fingerprinting powders that we mentioned in the first place. So in this case, the evidence is placed into a chamber and then super glue is placed underneath and heated to make the fumes leave from the super glue liquid and attach onto the sweat where the fingerprint had touched the object. In this case, we have a can of soda that clearly has fingerprints developing from the cyanoacrylate fuming method. So you get a white print there, and then you can photograph that print, but most commonly you would add powder and lift the print with tape after using the cyanoacrylate fumes to identify the area of the print. So there we have it, a chemical method used along with the standard fingerprinting powders that have been in use for even longer. Finally, the last topic that our text addresses is the collection and preservation of fingerprints. So again, as always, we want to photograph everything as much as possible, and in the case of fingerprints, you want to photograph the prints both with and without the scales, the rulers, to have both native and annotated photographs for all the prints. The print must be lifted if the item is not transportable. So if it's a large item, then you're not going to seize that whole item and bring it to the crime lab. Instead, you're just going to lift the print and again, of course, photograph the print as well, but have that be the physical evidence rather than seizing that item that's not easily transportable. If it's a smaller item, then you can certainly put it in an appropriate package and send it to the crime lab for analysis. If we are going to lift the print there, the print should be dusted, lifted, and placed into a label card that contrasts the color of the powder. So if your surface is light in color, then you're going to want to use a dark fingerprinting dust like we see here, the black or gray dust there. If it's a dark colored surface, then you'd want to use a light colored dust. or an ultraviolet UV active dust. So finally, the labeled card gets placed into an envelope and sent to the crime lab for analysis. So hopefully you've enjoyed our discussion of fingerprints and looking at the powerful analysis of those prints to personally identify individuals and hopefully get some leads in a criminal investigation. We'll pick back up with our next topic, so hope to be talking with you again soon. Take care, everybody.